So welcome everybody. Today we're gonna talk in lecture 6 about generative models for robotics. And I'm very excited to talk about this very important topic for robot learning today. Let's start with a quick recap of why we care about generative models in the first place. So the fundamental question, the fundamental issue in robotics, as we talked in the third lecture, is that the mapping from observations to actions is not a function, it's like really a distribution. And there are like two main reasons we covered why this, to kind of motivate why this is, right? The first one is like the stochasticity, right? So for example, with like this 7 degrees of freedom arm, we already mentioned that there are like infinite ways how we could kind of reach the same goal state. And the second one is like the inconsistency of experts, for example, when they collect demonstration, where there might be, many different modes, how they collect demonstrations for the same task, right? Maybe one day they like operate the robot faster, or they have like a different mood, or one day they do a side grasp, the other day it's like a top-down grasp. So there are many ways how to like achieve the same task and goal, right? And this essentially means that for our policy, we would like to learn a distribution over actions. And the generative modeling part comes handy to help us solve this modeling of the distributions. If you remember, like we already covered that when you train like a deterministic policy with behavior cloning, with the mean squared error, like the math will kind of force us to look for the average of all the demonstrations, right? So you might end up in the hitting the tree in the middle of the obstacle instead of going left or right. We kind of agree we need to learn like the full distribution, right? And the question is, how do we actually represent this high-dimensional multimodal distribution, right? And so today we will cover like kind of three families of generative models that try to answer this question from different angles, starting with the autoencoders that learn like a compact latent representation, then diffusion models that rather than encoding structure, explicitly learn to iteratively denoise to clean samples, and then we'll finish with flow models that learn a deterministic invertible transformation that maps a sample distribution to a complex data distribution. And we will also kind of cover how all these three are behind many of the advances in robot learning in the last couple of years. So before we dive into the specific architectures, kind of to make sure that we all share the same mental model of what we mean when we say like generative modelings, kind of the same underlying concept, no matter like if it's a VAE or a diffusion or flow or a GANs or anything, is that generative model is a learned transformation from a simple tractable distribution into a complex data distribution, P data. So typically, we will start with something easy, like a standard Gaussian from noise, and then we will want to map this into the target data distribution that we actually care about or model. So it could be like images of cats, like you see in this slide, or for us, roboticists could be like robot action trajectories. So one way to handle this multimodality question, we a little bit already like prefaced in the imitation learning lecture with the latent variable models, right? Which allows us to really index into different modes of the distribution, like go left or go right via this latent Z, where we can now say how to condition our policy on like going left or right. But we didn't really talk much about how we can actually train to compress, how we can learn to compress the expert's action into this latent Z, so we can learn this mapping. And this is where the architecture of the autoencoder comes in. And the idea behind is like pretty simple. You've probably seen this before. We have two networks, an encoder F5 that compresses the input X into a compact latent representation Z, and then a decoder G theta that takes that latent code and then tries to reconstruct the original input back with, for example, a L2 norm loss. And that's it. Like, we don't need any additional labels or anything, so it's pretty like self-supervised. And the bottleneck here in the middle essentially forces the encoder to learn like this compressed representation of the data, because the only way to achieve like a low reconstruction error is to preserve like the most important like features, let's say, right, of the data distribution. So this naive autoencoder can compress data, that's true, but it has some limitations. First of all, the latent space has no structure, so the encoder can place clusters anywhere it wants. There's nothing like forcing it to like enforce any structure in the loss or so. And the second one is the only regularizer is the size of the bottleneck itself, right? So the dimensionality of the Z bottleneck is what constrains how much information can pass through. But it doesn't say anything about how like this information should be organized, right? And then third, and kind of the probably like for us the biggest crucial limitation is that this is a deterministic model, right? So each input maps to a single point, and so there is really like no distribution really, and so this means that we also can't like sample new data at test time if it's deterministic. And so here is where the variational autoencoders kind of like come in to solve all three problems that we just mentioned. The key idea is that instead of encoding to a single point, we encode it to a distribution over Z. So specifically, the encoder in like the most popular case will output the parameters of a Gaussian, like a mean and a variance sigma, and then we sample Z from that Gaussian before passing it to the decoder. And then kind of to enforce the structure of in the space, we add a regularization term that forces this approximate posterior to stay close to our Gaussian prior. And so mathematically, our goal here is to maximize the log likelihood of the data, so log p of theta x. However, it's often, as we discussed also in the third lecture, intractable to compute this directly. So instead, we maximize the evidence lower bound, or the elbow. And so the reconstruction loss here is similar to the naive autoencoder, just that now we have an expectation as Z is not deterministic anymore. Right? So now we are asking, on average, over all the Zs I might sample, given this X, how well does the decoder recover the original X? And then the KL regularizer is what kind of like penalizes it from deviating too much from distribution. Maybe the key message here is that, or the key advantage is that now, in principle, at test time, we can sample any Z from our P of Z and then decode it into a meaningful output. So now we really have a generative model. But there is one problem that we have faced in the previous lecture too, that this stochastic sampling step is not differential. I didn't get the chance to really talk about this during the policy gradient derivation but here last week, but here it kind of appears again. So what we can do here is that instead of sampling Z directly from the distribution that the encoder predicts, we can rewrite it as a function, as a deterministic function of the parameters and an external source of noise. And so we pull a random vector, epsilon, from a standard normal distribution, and like this has like no learnable parameters. And then we define Z equals the mean plus sigma, and then like the element-wise product with epsilon. And you can see on the bottom like how now the computation graph pulls this kind of this randomness to the side. And so now from the perspective of the gradient, our mean and variances are just nodes in a standard deterministic calculation, and the gradient can flow. Okay, so we have seen like the nice graph and one formula, but why does this make sampling, the sampling operation differentiable? And so the core problem is that computing the gradient of the loss with respect to the encoder's parameters phi is difficult because the loss involves an expectation under a distribution that itself depends on phi. And so there are like two ways how you can handle this. The first one is what we saw last week, which is the score function estimator, which in RL we call reinforce. And here, like, you can use the same derivation we did last week with the log derivative trick to move the gradient inside. But one thing to notice here is that in this formulation, the gradient only acts on the log of the Q term, ignoring completely how the Z itself changes with phi. So this means that this will have very, very high variance because the gradient has no way to see into the function of Z itself. So basically, the optimizer will be kind of guessing because it knows if a sample was good or bad, but it doesn't know how to shift the mu and sigma to make it better. And the second option is the reparametration trick that we just covered, where by rewriting and substituting Z with the formula from the previous slide, we can see that P of epsilon is now completely independent of phi. So we can move freely the gradient inside the integral again, similar to last week, because it's a linear operation and using a Leibniz rule. And once it's inside, we can convert this back into an expectation over epsilon. So which in practice means that we can now sample one epsilon, compute the gradient, and that's it. We're done. Yeah. Okay. And yeah, so exactly. So the key thing here kind of to remember is that now with this, we can kind of, the gradient of the loss with respect to phi now equals to the gradient of f with respect to z. So this means that this is coming from the decoder, and it tells us which direction like we should like move or update our z. So it kind of directly tells us like how our encoder parameters will influence our latent. Cool. So after all this math, what did this actually buy us? So if we look at this now, the latent space, and compare it to the previous encoders, we have now a more continuous and structured latent space. And it's generative because now we can sample Z, and like the decoder will produce meaningful outputs. And at test time, we don't even need the encoder for generation. We can just simply sample from Z, from our prior distribution, and then use the decoder. So although variational autoencoders are powerful, they don't come without limitations. Concretely, it has two kind of common failure modes. First, if you have like a powerful high-capacity decoder, in principle, it could also try to learn P of x directly. So this means that it could learn to completely ignore the latent set that you are passing to the decoder. So in this case, your model will become like a deterministic model once again. The second one is a bit more subtle. It's what's called the prior mismatch. So imagine we have trained our model on these two modes of going either left or right, right? And now imagine that at test time, and this works beautifully, we have trained on this, and now at test time, we sample a set from our Gaussian prior that lands in the middle, in between left and right. Now the issue is that the decoder has never seen a latent in that region because we had no demonstrations, right? So even though our math kind of forces our latent space to be continuous, the decoder will, in that case, like hallucinate, something that will be completely wrong. And this is especially a big issue in robotics, where you don't want to be hallucinating like unsafe actions, for example. One way to alleviate this issue is by replacing the continuous Gaussian latent set with a discrete codebook of k learned vectors in what are commonly known as vector quantized VAEs. So the intuition behind this is simple. Imagine you have a dictionary or a codebook of k learned vectors. Now when the encoder looks at an image and produces a continuous vector, we don't pass that continuous vector to the decoder. Instead, we perform a nearest neighbor lookup. We find the vectors in our codebook that are closest to it, and then pass that discrete code to the decoder. The encoder now essentially is forced to commit to one discrete code rather than producing a Gaussian distribution, and this kind of eliminates this posterior collapse we just mentioned before. And so also there is no KL divergence to minimize, and no way for the decoder to ignore Z, because the Z is now kind of a hard discrete selection. Mathematically, we are performing a quantization with this arc of min lookup operation. But again, this is kind of a recurring pattern, like this is not per se a differential operation. So concretely, this means if we nudge a bit our latent, let's say like the Z to the left or right, then in principle, the closest neighbor will be still the same. Because arcmin is a piecewise constant function, so it means effectively the gradient is like 0 almost everywhere. So how do we fix this? So in practice, we used a straight-through estimator, which in essence just says, let's pretend the quantization step didn't happen during the backward pass and pass the gradients along. So the high-level intuition of this is that if ZQ and ZE live in the same embedding space, then by definition, they will be very close to each other. So the gradient that tells the decoder how to change ZQ to reduce the loss is probably a very good proxy for how the encoder should have changed ZE, so like the latent produced by the encoder, in the first place. So this means that we essentially copy the gradient from the decoder's input directly back into the encoder's output. Yes, and here the SG in the formula stands for the stop gradient, which acts as an identity in the forward pass, but has 0 gradient in the backward pass. And and here you can see now how that kind of like resolves in the backward pass to copy the decoder's gradient directly to the encoder. Cool. So how does the loss for training the VQ VAE look like? So we have the standard reconstruction loss on the left, where the encoder and decoder are trained jointly via this straight-through gradient estimator. Then the second term is the codebook loss, which moves the codebook vectors towards the encoder outputs to essentially learn a representative like kind of vocabulary of the data distribution. And then finally, we have the commitment loss. So for this kind of proxy gradient that we just talked about with the straight-through estimator, in order for this to stay valid, we need to make sure that like the ZE and ZQ, so the encoder's latent and the quantized version, actually stay close to each other. So without this penalty, the encoder could output values that are very far away from the actual codeboot vector. All right, so this training gives us a codebook and a decoder. But the question is like, okay, like how do we actually like sample, how do we generate like new data at test time, right? Because this doesn't seem to produce it. So in order to do that, to generate new data with VQVAEs, we have a second training stage. So the idea is pretty simple. So concretely, once we have trained our VQVAE, we run this through our data set and collect the sequences of code indices that our encoder picked. So this means we're essentially translating our data set into a sequence of discrete tokens. Now, the second training stage consists in training a prior model over this sequence code. Typically, this could be, let's say, an autoregressive transformer. And so then this model will learn, like given some initial first codes, what are the next most likely tokens or codes, right? And then we finally get to the inference stage, right? Here, we will now sample from our prior, let's say like our autoregressive transformer model, then do a lookup from the indices to the vectors, and then use our decoder trained in the first stage to generate a clean sample of data, like an image or robot actions in our case. So to wrap up this section on autoencoders, here's a visualization of how the latent space evolves across these three formulations, or the variants we discussed. VQVAEs have fixed most of the issues we presented, like the posterior collapse or the prior mismatch. They still have some issues like codebook collapse, which means that, for example, it can be the case that many codes go unused during training because the encoder converges to just using only a small subset of k vectors. This is why nowadays people use, for example, FSQ, finite scalar quantization, as a more robust alternative, but we don't have time to go into the details of that. And some other limitations are like you need to know in advance the size of your codebook, for example. And even with discrete codes, mean-seeking behavior at the output level remains if our reconstruction loss still uses MSE. So you can still get like blurry face images, for example. To summarize, VQVAEs turn continuous signals into discrete tokens, enabling transformers to reason over observations, actions, and behaviors in a unified token space. In robot learning, you can find them across many different applications. For example, they are very popular for tokenizing images and videos, as you can see on the left side. In models such as Gaia for self-driving or Cosmos video models. They're also quite popular for latent action learning, where works like LAPA or Genie use VQVAEs to quantize the movement between frames of games or egocentric human videos, and to translate then these latent codes into robotics. And my own work used it to quantize latent plants from play. And finally, on the right side, you can also see VQVAEs are also used sometimes to discretize continuous robotic actions for VLAs and such. All right. So we have seen that kind of like VQVAEs have still this limitation of having like mean-seeking behavior in outputs when we use the MSE loss, right? So rather than learning a compressed representation of the latent space and decoding from this space, diffusion model asks, what if we learned directly to model the full continuous distribution over X without any bottlenecks at all? So on a high level, the diffusion has two processes. During the forward pass, we take a clean sample, like this image of the cat on your left. And then iteratively add Gaussian noise until all information is lost. And then on the backward process, we train a neural network to denoise that static, step by step, to learn to recover the clean image from that noise. Now, by framing this problem this way, we aren't asking the model to guess like the image in one shot, but we are asking it to make small incremental corrections, which is a much easier learning problem than doing everything in one go. Okay, we'll look a bit into the details of how these things work now. So for the forward process, as I just said, like we are iteratively adding data. If you look at the equation, we define the next state as a weighted sum of the current state and some additional noise, random noise. The first term is in the equation, the signal decay. At every step, this means we slightly shrink our current sample, pulling it a little closer to 0. And then the second term is the noise scale. The term beta I is what we call the noise schedule or the variance schedule. It's a hyperparameter that determines exactly how much noise we inject at every step. And notice we're using the reparametrization structure here again, writing the noisy sample as a deterministic function of the current state, plus some fixed noise variable. We will see the benefits of this in a couple of slides. Okay, what about the reverse process? In principle, the reverse distribution is intractable, right? Because infinite clean images could have produced the noisy version, right? There is no way to know like which one is the correct one. So here is a key insight that makes diffusion models actually trainable. Instead of asking the network to predict the previous image, so x I minus 1, directly, which is a hard kind of ill-posed problem, we ask it to predict something much simpler, the noise that was added. Specifically, we train a neural network that takes the noisy image and the time step as an input, and then predicts the noise that was added at that step. So, and as I said, like, why is this a better learning problem? Because noise is just a sample from a standard Gaussian, and so it's like a really like clean, like easy regression target. And because we know exactly how much noise was added during the forward process, we can train this with a simple MSE. Loss between the predicted noise and the actual noise. And as aforementioned, like each individual denoising step is a small kind of like local correction and much easier than having to predict everything in one go. So let's look at the training objective. And you'll notice immediately that it's kind of the same elbow objective as in the variational autoencoder case, just that we extend it now across t steps. So there are 3 terms. The prior regularization, it ensures that after t steps of noising, the end result will look like our Gaussian prior, and this is kind of satisfied by construction during the forward pass. So in practice, we don't need to learn it. Then the reconstruction term, we already had this before. How well can we recover? And then the big sum in the middle is the denoising matching terms. So this asks, like, at each time step, how well does our learned reverse process match the true reverse? One thing to note here is that now, because the forward and reverse distributions are Gaussians with the same variance, their KL divergence simplifies to the L2 distance between their means. And So with a bit of math, you can derive then what they did in this paper, denoising diffusion probabilistic models, to this kind of more simple term that you can see at the bottom. Essentially, like they realized that you could throw away like complex weighting coefficients from the elbow objective and just minimize the mean squared error between the true noise and the predicted noise. All right, so now if you look at a formula to actually compute that loss, there is kind of like one small issue, and that is that the formula says that we will need to teleport from our clean data to some arbitrary sample noise state without iteratively doing all the previous steps. Let's say like 500 steps, which would be then also like OT complexity, right? So here in the slide, you can see the derivation of how we can enable efficient training. We first, for convenience, define alpha, the signal retention, as 1 minus beta, and then start by unrolling x1 and x2. Then we substitute x1 into x2, and then we get this mess of square roots on the right side of the slide. Now, the key thing here is that the two noise terms both come from independent Gaussian distributions. And we use the key property that the sum of two Gaussians is also a Gaussian. So the two noise terms can collapse into a single noise sample epsilon. And then when you generalize this to I steps, the signal coefficient becomes the product of all the alphas. And then this gives us the final form that allows us teleporting from x0 to any noisy xy in a single step, enabling fast training. So now let's look at how we actually can generate, sorry, we'll do questions after, if that's okay. How we actually generate samples with this trained diffusion model. And so the first one is like the DDPM sampling procedure, where we start sampling Gaussian noise, then iterate from t down to 1, and then at each sampling, and at each denoising step, we apply this formula that you see on the slide. The first one is we predict the predicted mean. So we take xy, subtract the predicted noise scaled, and then renormalize. And so this is kind of the deterministic denoising step. So moving towards where we think x0 will be. And then the second step is kind of a little bit more interesting. This is, we add some stochastic Gaussian noise. And so like you might be wondering, okay, this doesn't sound like right at all, right? So we are kind of like denoising, but like why are we adding like noise back in? And so this is a little bit subtle but important, because if we run this process purely deterministically, all samples starting from different xt's would tend to collapse towards the same mean. And so the injected noise kind of maintains the sample diversity, ensuring that we explore the full distribution rather than always generating the same average output. Okay, and then kind of like in practice, so DDPM can take a long time to denoise. Like an image, for example, it could be around like 1,000 steps. So it's really slow and therefore also like difficult to apply in robotics, where we care, for example, about real-time control. DDIM solves this issue by decoupling the number of denoising iterations in training and in inference. The key insight is that instead of kind of stepping through all the time steps, we define a small subset, maybe let's say just 20 steps instead of 1,000, and then jump in between. And then in each step, we use our our trained noise predictor to do something a bit more clever. So we use the inverse of our teleportation formula from before to estimate what the clean image would look like based on our current noisy state. And then once we have that estimate of the target, we renoise it just enough to reach the next step in our subset. So for example, jumping from like T100 to 80. And the key thing here is what is actually missing. So in DDIM, we don't have a noise term. So unlike DDPM, which adds this noise term back at every step to keep things stochastic, DDIM is deterministic. And so this allows us now to essentially, at inference time, to use much fewer denoising steps to produce a clean image or a robot action. One thing to notice is that everything we've covered so far is unconditional generation, right? So we are sampling from our P of X, the marginal distribution of our data, with no control whatsoever over what comes out at the end of this generation process. And in practice, this is usually almost never what we want, right? So in image generation, we want to condition, let's say on a text prompt, or for our robots, we want them to solve like a task. There is a simple fix on how we can achieve this, right? So we can just pass along like a conditioning information C that can act as an additional input to the noise predictor, and then we can keep like the entire training procedure the same. Conditioning on C sounds simple, right? Like we can just pass it as an extra input, but there is a subtle problem. The model, again, similar as in the VAEs, can learn to ignore the condition and learn to denoise unconditionally anyway, since that's often the easier optimization path. Kind of in the literature, the first kind of solution to this was classifier guidance, which required training a separate classifier, like P condition given X, at every noise level, which is quite expensive. There is nowadays a different trick that's usually more popular called classifier-free guidance, which solves this with a kind of a more elegant trick. So during training, it means what they propose is that they randomly drop the condition information with some probability, replacing the condition with like a, let's say, null token or something. And so essentially they are forcing the network to learn both the conditional and unconditional generation simultaneously. And then at inference, they kind of blend both predictions. So you start from the unconditional prediction and then add the guidance scale times the difference between the conditional and unconditional predictions. And that difference is essentially the direction in noise space that the condition is pushing us, and this W is the guidance scale, which controls how hard we move in that direction. In image generation, for example, increasing this guidance scale a lot will give you like sharper, more prompt-consistent images, but at the cost of less variety and diversity. All right, so we've talked a lot about like kind of the math behind diffusion. Let's see how this comes together in robot learning, in an actual robot system. And so the first kind of case study that does this is diffusion policy from Changqi in 2023, who, by the way, will be today's guest speaker. The key insight is actually rather simple. Everything we just derived for image generation applies directly to action generation. So we just replace pixels with robot actions. Instead of denoising an image, we denoise a sequence of robot actions, AT. The training objective is exactly the same. So we use the DDPM loss for training, DDIM for faster inference with less denoising steps. And then crucially here, the observations, like the current camera image, or the robot state get injected directly into the noise prediction network as a condition. The best part is that unlike previous works, the proposed approach also doesn't require any future state prediction. So it doesn't have to predict future images or anything. So it's quite more efficient. So the policy directly outputs the sequence of actions conditioned on the current observations. Maybe I'll go a bit more quick over this. The first thing to notice here is that the observation is computed only once before k denoising steps, right? So we don't have to recompute this at every step. This is quite crucial for efficiency. And then for the noise prediction, they use a 1D temporal unit, treating action sequence like a 1D signal over time, and then they inject the observation conditioning via film conditioning, so feature-wise linear modulation that learns to shift and scale the activations of the unit based on the observation embedding. And then they also presented a transformer-based version which uses cross-attention to condition the action denoising on the observation tokens. And one thing to notice here is that diffusion policies really handle multimodality quite well. And in general, we've seen tremendous progress. They work really well also in real robotic systems. But they have one challenge, that they are really specialist models. They work very well to fit a single task, but have proven to be a bit more difficult to scale, to learn more generalist or multitask policies. And especially the transformer-based version from the original diffusion policy is quite brittle and sensitive to hyperparameters. There are a few kind of follow-ups that try to address some of these limitations. For example, we will talk more about this later when we talk about generalist policies. But for example, Octo, which trains a high-capacity transformer network on 800,000 robot trajectories, and then defines this readout tokens that compresses the observations and tasks, and then attaches a conditional diffusion decoding head that attends to this readout token that summarizes the previous information, and then really can condition both with natural language or goal image observations, for example. Another interesting follow-up is the IT block policies, where the key architectural innovation is replacing the cross-attention for conditioning with adaptive layer normalization, or ADALN0, which is borrowed from the diffusion transformer literature for image generation. So here, instead of having the observation tokens attend to action tokens through full cross-attention, the conditioning information is injected directly, modulating the scale and shift parameters of the layer normalization inside each transformer block, as you can see on the right. And this is kind of more stable for training, and really scales empirically much better. And as you can see, this also allows handling really long horizon dexterous manipulation tasks such as sushi cutting. All right, so now we move off to the third and final framework, flow matching. Until now, we've been kind of destroying data with complex kind of noise schedules. Flow matching instead asks, why not just draw a straight line between the noise and the data? So instead of predicting the noise vector, here we learn a velocity field that transports samples along along continuous paths from noise to data. And the path that we choose here is a straight line formulation. So this means that at T0, you have pure noise, and then at T1, you have kind of clean data. And the benefit is that we have no complex noise schedule to tune, so it's just really a straight deterministic path. The ground truth velocity is a vector that points directly from the noise to the data. And we train our network to predict this velocity at any given time t. So this means that at test time, we don't denoise in the probabilistic sense. We actually are integrating. So we start with noise and then use an ODE solver, for example, like a Euler step, to follow our learned velocity towards the data. And yeah, maybe one thing to notice is also the relationship between these. So, for example, if you have a linear schedule, then flow matching and diffusion are actually equivalent. So diffusion predicts the noise, and flow matching predicts the velocity, but they are related by a simple reparameterization. In general, flow matching straight lines are much easier to learn, and they require fewer integration steps. And as I said, they don't have like very complex noise schedule hyperparameters, and this is why it's kind of like been replacing diffusion as the go-to framework in both image generation and robot learning. So flow matching already gives us straighter paths than diffusion, but there is still kind of like one subtle problem. When you randomly pair noise samples with data samples, the straight lines between them might cross each other. And when the trajectories cross, then the velocity field has to represent conflicting directions at the same point in space, which forces the the learned field to curve. And so this means that this will then like kind of slow down like integration. So rectified flow kind of is one solution to this problem. And they show how to do this with a kind of iterative procedure where you train a flow matching model once, then use it to generate couple noised data pairs. So you sample noise, you learn, run the learned flow to get the corresponding data point. Now you have your pair of like x0 and your epsilon. And they are now kind of naturally attached by this flow vector, right? And now what you do is you retrain on these coupled pairs. Because the pairs are now matched by the flow itself, the trajectories kind of untangle, and the crossings get eliminated. And the paths become really straighter. As you can see in this visualization that kind of shows the path between the original flow matching and the rectified flow. All right, in robotics, Pi0 from Physical Intelligence was the first model to, as far as I know, to adopt flow matching. Concretely, they fine-tuned a VLM to produce actions via flow matching. So this was kind of, as far as I know, the first flow matching VLA, which now has become kind of like the standard for or default for most VLAs. One nice technical detail here is that instead of sampling the flow time uniformly during training, they propose sampling this from a shifted Vita distribution that focuses on the noisier, harder time steps. So where action prediction should be more difficult and where the model needs to predict more. We will talk more about VLAs and journalist policies in lecture 9. All right, so to conclude, today we have covered 3 families of generative models, each answering a different question about how to represent complex data distributions. So we started with latent variable models, so autoencoders that gives us compressed representations via reconstruction. We then saw how to add kind of more probabilistic latent spaces via reparameterization, and also with VQ-VAEs, how to discretize them into a learned codebook. Then with diffusion models, we've seen with DDPM how to iteratively noise Gaussians into data. with DDIM, how to make this faster and deterministic by discretizing probabilistic flow ODE. And then with classifier-free guidance, how to steer generation by blending conditional and unconditional predictions. And then finally, with flow matching, we have seen how we can learn velocity field that transport noise along straight paths and rectified flow that straightens those paths further for even fewer integration steps. The key takeaway for robotics is that we started this lecture with this simple observation that robot behavior and action prediction is inherently multimodal, and with MSC regression and deterministic policies, this will fail. And everything we've covered today, from VAEs to diffusion models to flow matching, is kind of the tools we use in some of our latest and greatest robot policies. Yeah, with that, thank you for your attention. And yeah, let's switch to the papers.